Hello, let's continue our progression through the material here on essentials of computer architecture organization. And what we're going to be talking about today is chapter 3. This is data and program representation. And so this is an interesting area where we start to figure out what do those ones and zeros mean, and how do we convert things from a computer's language and alphabet at a very low level to things that we would be familiar with. What do those bits represent? And there's various ways of doing that. So let's first refresh our memories about digital logic. It's built on two-valued logic system, binary 2, base 2. You can look at it a couple different ways. And so how do we interpret things when something is positive, when it has a positive voltage versus something that has 0? You can be thinking of it in terms of high and low, true and false, asserted and non-asserted, say from a logical propositional point of view. And underneath, at the hardware level, this is all just electronics and wires, but that's not what we're trying to just deal with. We're trying to apply that in certain ways. So this gets into data representation. It's we build on digital logic, we apply familiar abstractions, and as a result, we come up with methods to interpret sets of Boolean values, whether they be numbers, whether it be some type of character, say the letters of the English alphabet, whether it refers to some type of address. One area in memory refers that we're supposed to jump to a block of other memory locations. And once again, it is just all bits, but it goes way beyond that. So we can have direct representation of digital logic values. We can assign mathematical interpretation, whether it be 0 or 1. And we can do things, we can take multiple bits together to represent complex data items. We'll show examples how they can mean characters. You need more than one bit to show all the different letters in the English alphabet. You may be looking at numbers with many digits, etc. So the same underlying hardware can represent bits of an integer or bits of a character. So it's all, we have to be able to know what those bits mean, and by looking at the data, we can interpret whether it is supposed to be an integer or if it's supposed to be a character. There's a concept called a byte. And so we have bits, which is one single digit. Bytes is a group of bits, and the size depends on the computer. Some examples of byte sizes. Here are 3 examples. I will be focusing a little bit more on what IBM uses, and we'll be talking about Ascii code and some extensions of that where it uses 8 bits. But there's other kind of things that have been around that uses different number of bits to encode. And so we typically use the word byte. If you buy a hard drive, you'll hear numbers like in megabytes, terabytes, gigabytes, and there's this is a word that you're probably familiar with. And typically for that convention, they talk about, they're referring to an 8-bit byte. So on most computers, the byte is the smallest addressable unit of storage. And following modern convention, we will assume an 8-bit byte, and that's what I'm just was talking about. So in terms of byte sizes and values, a number of bits per bytes determine the range of a value that can be stored. Bytes of k bits can be stored in 2 to the k values. So here's some example of what that plays out. 6-byte 6-bit bytes can store up to 64 possible values, 2 to the 6. 8-bit bytes can store 256 values, so 2 to the 8 is 256, and so that's what that's referring to. Well, we think in binary, and so we need to have some way to convert between these two systems. Bits themselves have no intrinsic meaning. Bytes merely store strings of ones and zeros, okay, but here something to think about: all possible combinations of 3 bits. So here are the possibility of how you can store 3 bits. There's 8. So there's 8 values that can be stored in 3 bits. So that's interesting. Um, so what are some of the possible interpretations of 3 bits? Um, we can think in terms of device status. So each of these bits is just referring to one thing, and we're not putting those together in some way. The first bit has a value of 1 if the disk is connected, 2, a value of 1 if the printer is connected, 3 has a value of 1 if the keyboard is connected. So sort of a check to make sure that you have everything connected that you would want before you start doing computations. You could have an integer interpretation where have a positional representation that uses the base 2, and it could range um, values from 0 to 8. Once again, we're talking about 3 bits, and so we must specify the order of bits. Um, Here is giving you some perspectives on a binary weighted positional interpretation, where each of these bits, even if you think in like base 10, where we're familiar with this, so you could just like pretend for a second that this was base 10, what value this would mean. Typically, we wouldn't put this 0 in front of it, but you have a number, and each one of them, the second digit would be 10 times that number. Well, for in bits, in base 2, you're using 2. So it's 2 to the 0, 2 to the 1, 2 to the second, and you're seeing that here. And it's either you have 1 or 0 for each one of those. And so with this value, you can see here it's spelled out. That is equal to 21 base 10, the way that we're used to computing it. So a set of k bits can represent integers from 0 through 2 to the k minus 1. So that's how many bits it can actually represent. This might be useful for you just to get familiar with some of these basic powers of 2. 8 bits to 256, we talked about that. And once you start to get familiar with this pattern, you'll be able to quickly be able to have some remembrance of what these different values are. So 8 bits would be useful, 16 would be another thing that's useful, etc. Um, Another common form of notation is what's called hexadecimal. Hex means 4, so it's 4 digits that you group together, 4 binary digits. It's easier to write than binary. You can only have to write 1 character instead of 4 characters, and each hex digit codes 4 bits. And so using decimal, you run out of values, and so that's where we start to use letters. And so it goes from 0 to F is how you specify things in hexadecimal. So it's just another way of, in a more efficient way, to represent bits. So in terms of hexadecimal constants, you can start to have these values mean something here. And so this is getting towards one computer, a DEC, digital electronics that had a form of encoding, and so this is the way how it would encode this. DEC 90949, and so that's how it is, and so we're grouping these things in 4 bits each. Well, if we want to encode symbols into bits and those bits put it into bytes, we need to come up with a convention that everybody agrees to. And here are some 3 examples. Epsidic is one, Ascii is really quite common, and Unicode is an extension of Ascii to have international and special characters put into a conventional set that everybody is familiar. Epsidic is something that IBM created, and if you were to purchase an IBM mainframe, Kummer was stating that you still would be using this format. And so if you wanted to encode the lowercase letter a, this is the actual value of what it would correspond to. Ascii is another very common one that I'm pretty familiar with, and I think as a result of this class and other encounters, you will get familiar with it as well. It stands for the American National Standard Institute, and it was adopted by PC manufacturers, and so that's the reason why it will be familiar to you, and we will come back to that later. So it specifies 128 characters. So here, the letter A, this is how it is assigned the value, and you can see how that's different than the Epsidic. Epsidic starts with a 1, it ends with a 1, the rest are zeros, and this is the coding, which is different. So it also has unprintable characters used for modem control, and so there's a few other things that are included. And this is the full ASCII character set. And so you have the hexadecimal representation and what is it that it actually corresponds to in terms of English. And there are some additional characters of different sorts that are also included, which I won't go into at this point. So Unicode is a way of extending the ASCII to not just have 128, but actually have 256 characters. So instead of 8 bits long, it's actually 16-bit long. So it can represent a larger set of characters. And the motivation is that it can accommodate a variety of languages such as Chinese. And if you've ever installed an operating system, say some version of Linux or maybe BSD of some sort or something like that, you'll oftentimes be asked to specify what language you want to have it in. And this is where it's starting to give information like, well, what is a keyboard designed for, and how are you going to be using some of those extra 8 bits. So that's in terms of character representation. Now, how do we deal with integers? Each binary integer is represented by a number of bits, so k bits here. So computers can have k from a number of different register size, say going from 8 all the way to 64, according to this example, many computers support multiple integer sizes. So you can actually flex. Maybe you only need 16, and there's other times you may need 64. Say for a floating point or just an integer, you really don't need as many bits unless it's a really long integer. So there's 2 to the k possible. Combination exists for k bits. And so the positional interpretation produces unsigned integers. So what does that actually mean? So unsigned integers is a straightforward positional interpretation. Each successive bit represents the next power of 2. Fortunately, this provides no provision for negative numbers. The precision is fixed to the size of integers as a constant. Arithmetic operation can produce overflow and underflow. Um, results cannot be interpreted in k bits as a result. Overflow can be handled with wraparound and carry bits, so there's ways of doing it, but in terms of precision, you're going to be limited. And so here's an example of an overflow. Say you're trying to add 2 digits together, and all of a sudden, the most significant digit, it gives you a 1. Well, this would be an overflow. And so how are you going to deal with that? It could just give an error and raise an exception. And so somehow that needs to be dealt with. So what about numbering the bits and the bytes? What type of order are you going to use? And this has not always been done the same way. And so we'll get a chance to get some insight into that. So we need to choose order for storage in the physical memory and transmission of that data over a data network. So we have the bit order and we have the byte order. How do you, the bit order is handled by the hardware. Usually this is hidden from programmers, and then the byte order affects these group of bits, say 8 or 16. So how it affects how you would interpret and come up with what the integers are. And this is visible and important to programmers. And so that's something to consider. In terms of convention and names, little endian places the least significant byte of integers in the lowest memory location, and big endian places the most significant byte of integer in the lowest memory location. So most significant in the lowest memory is big endian. Least significant, lowest memory location is a little endian. And a historical note that Coomer brings out is DEC, Digital Electronics Corporations, once used an ordering with 32-bit integers divided into 16-bit words in big endian, so that's here. But then if you looked at the bytes, those uses a little endian. So there's a big endian, little endian combined in the ordering scheme, which was quite complicated. So here's an illustration of big and little endian byte order. And so it's, in terms of hexadecimal, it's nice to group things in terms of 4 bits. And so this is color coded to try and make this a little bit easier for you to see. But what we are trying to show is integers for 497, 171, 303, and binary positional representation. And we want to look at what the difference would be in little endian and big endian. And so we see that this one here at location I plus 3 in the big endian is the same as location I in the little endian, and then vice versa. So these two are in opposite order. So this is something that you're going to have to know what the conventions are, especially if you're trying to share data between computers, and you'd have to have a proper translation to make things compatible. So another possible way of coding integers is to have signed binary integers. Signed arithmetic is needed by most programs. There's a variety of different representation possibilities. And each has been used in at least one computer. Some bit patterns are used for negative values. And there's trade-off. Unsigned representation cannot store negative values, but can store integers that are twice as large as a signed representation. So And then we have, well, what is a encoding convention? And here we have three possibilities: sine magnitude. You have one bit that either says it's positive or negative, one's complement, and then two's complement. And I'll show an example of what that means in the next couple of charts. Sine magnitude representation is most familiar to humans. The first bit represents a sine. Successive bits represent absolute values of integers. And so, interesting quirk here with this kind of encoding scheme is you can create a negative zero. So you can have a positive zero and a negative zero. One's complement, what's the convention it uses? The positive numbers uses positional representation. Negative numbers is formed by inverting all of the bits of positive value. So what would that mean? So if we have this as a representation of 2, the one's complement means that you invert all of those digits, and so thus this would be -2. So here we can have 2 representations for zeros, either all zeros or all ones, and both of that would mean that that is supposed to be a 0. And an interesting note, internet checksums typically use one's complement. Two's complement, it's a little bit more complicated. The position number uses position representation. The negative number is formed by subtracting 1 from the positive value, inverting all the bits of the result. So here we have the what's is +2. And so the first thing we would do would be subtract 1. And so that means that this would be 0, 0, 0, 1. You invert that, and so we get 1, 1, 1, 0. The higher order bit is set if number is negative. So we don't have a balance between negative and positive values. There's one more negative value than positive values with this type of encoding. And here is something that you can actually use more than one of these coding schemes together. Then you can use both the unsigned and two's complement. This is used together because a single piece of hardware can handle both of these together, and software can choose an interpretation for each integer. So an example using 4 bits, adding 1 to binaries 1001 produces 1010. The unsigned interpretation goes from 9 to 10, and the two's complement interpretation goes from -7 to -6. May not really something you have to memorize, but it might be nice to look this over, that here you have these binary strings, and as a result of these 4 encoding schemes that we've talked about, here would be the actual representation. And so you can see how they vary. You can have no sign. You can be going from positive to negative and have 2 negative, either a positive or negative 0. We see situations for that in these 2 situations. And the 2's complement avoids that. So that's just a little bit of convention for you to be thinking about. Sine extension. What do we do for some of these cases here? This is needed for unsigned and 2's complement representation. It's used to accommodate multiple sizes of integers, and it can extends higher order bits known as sign bits. And so if you get these extra bits, what type of convention are you going to be using so it's not confusing and it's consistent? So so let's assume a computer, so it's say it supports 32 and 64-bit integers. And we're using 2's complement representation. When 32-bit integer is assigned to a 64-bit integer, the correct numeric value requires the upper 32 bits to be filled with zeros for a positive integer, ones for a negative number. And in essence, higher order sine bit from 32 bits must be replicated to fill higher order bits of larger integer. So let's show an example of a sine extension during assignment. So first we have the 8-bit version, and I color-coded this again in 4 bits just to make it a little bit easier to see. And for the 16 bits, you just literally you replicate what was the most significant digit, either a 1 or a 0, and that's just replicated all the way to the end. During the assignment to a larger integer, hardware copies of all bits of a smaller integer and then replicates to the higher order sign in the remaining bits, like I just explained. And so this is just the summary of that, and we saw that already on the previous chart with an example. So what about having sine extension during a shift operation? Right shift of a negative value should produce a negative value. So if we shift to -4, 1 bit, it should produce -2, which you can also think of it as dividing by 2. Using the 16-bit representation for -4, if we shift it to the right one, we need to add and replicate the higher order bit to make sure that that still is clear. So what are some of the consequences for programmers? Most computers use 2's complement hardware, which performs sine extension. The same hardware is used for unsigned arithmetic, which means that assigning an unsigned integer to a large unsigned integer can change the value. To prevent errors from occurring, a programmer or a compiler must add code to mask off the extended sign bit. And so this just gives you an example in a higher order language of how you could be dealing with that. IBM pioneered this idea of a binary coded decimal BCD. And so it represents integers as a string of digits in an unpacked form, 1 digit per 8-bit byte, and packed 1 digit per 4-bit nibble. And so we have another term that is not used so much as a nibble would be 4 bits, and a byte is most commonly thought of in terms of 8 bits. So it uses unsigned magnitude representation. And so here are some example of unpacked BCD. So if we wanted to do the number 1, 2, 3, 4, 5, we have this kind of a nomenclature. And then in terms of an integer 1, 2, 3, 4, 5, 6 is stored as what's listed here. So anyway, I'll just leave that for now. Does it make sense to go ahead and using BCD? Does it help? It takes more space, the hardware is slower than integers or a floating point. The example is it gives results in humans expect, say in something that we would see in Microsoft Excel, and it avoids repeating binary values for 0.01 and stuff like that is preferred by banks, at least historically. Well, now we've been talking about integers, negative integers, positive integers. Now, what about floating point, where you have scientific notation where you have a number and then an exponential base 10. And so Avogadro's number is an example. In scientific notation, this is what it would look like. So what is a hardware? How would it start to deal with it? Hardware uses base 2 instead of 10, so we're not going to be having 2 to the 10th. I mean, we're going to have 2 to something rather than 10 to the something. Hardware allocates fixed size bit strings for the exponent. That's what this is called. If you don't remember the mantissa, this is the mantissa. So how do we optimize floating numbers in a notation that would be useful for computers? So we normalize the mantissa. So we get rid of any leading zeros. And so the first digit is not supposed to be a 0. No, so there's no need to store most significant bit because it is always 1. 0 is a special case. And the exponent allows negative as well as positive values. And there's an ability in this to permit rapid magnitude comparison. There's an IEEE standard that defines what the single precision and double precision represents. These kind of standards are helpful to make sure that we're all talking in the same way. And so here is a 32-bit standard, and here is a 64-bit standard. So we have a sign bit, we have the exponent, and then the mantissa for each of these cases. And these are the layouts of the specific bits. So special value in the IEEE floating point, there's a 0, positive infinity, and negative infinity. Infinity values handle cases such as a result of dividing by 0. You probably have done some programming and sooner or later bumped into getting an error message where you result in getting the infinity. And so this is where stuff like that would show up. So in single precision range, you can see how, relatively speaking, it has a modest range. And here is the decimal equivalent. So 10 to the minus 38 to 10 to the plus 38. And with terms of double precision, we can see that it's a huge advantage in terms of the range, orders of magnitude greater. And so that's the reason why that would make a lot of sense to use. Here we just walk through an example of a floating point value. Consider the decimal value 6.5. In binary, 6 is 110, and 0.5 is 0.1. So that would give this kind of a number, 110.1. So if we normalize that, this is what we would get, a 1.101 times 2 to the 2. So this would be in a scientific quote format. The sign bit is 0, so that would be positive. The exponent is biased by adding 127, giving 128. That's because we have this 2 to the second. We're trying to encode this, the 6.5 in scientific notation. And the leading one of the mantissa is stored. It's always 1, so we're just coding these digits here. And so that we see those 3 digits. And so that's just a little bit of insight of how that works. Okay. In terms of data aggregates, so it's typically arranged in contiguous memory. And so here would be a struct. And if you've done some C programming or something like that, that might be a term that you're familiar, some type of a structure. And so just by incrementing at a predictable amount of in the memory, you're going to go from integer 1, 2, and 3. And so if you're trying to iterate, that's a very useful thing to have things ordered in that fashion. So just to finish up here, in this chapter, we've talked about fundamental value in digital logic, what it is. It's a bit. And then we looked at different ways of grouping those bits to represent things. Integers, we talked about that. Characters, such as the Ascii character set, and floating point values, where we have a mantissa and an exponent, and various ways of how you would consider those. We walked through an example of that. We talked about how integers can be represented. We talked about Sine Magnitude, which is the easiest way for us to understand it, but not necessarily the most efficient in a computer. We talked about one's complement, which isn't generally used, but it's used as a parity check. And finally, the two's complement, which is the most common. And so that's a quick look at those. One piece of hardware can be used for both. And so we showed had a discussion on two's complement arithmetic and unsigned arithmetic, that we can have a way of using multiple encoding schemes and not have it be confusing in the computation. And bytes of integers can be numbered in big endian order or little endian order. And so how are you going to stick the bytes either ascending or descending? And so those are two possible ways of doing that. Organizations such as Ascii and IEEE define standards for data representation. And we were using an IEEE standard for single and double precision that we showed the 32 and 64-bit examples of how that would look. So thank you very much. Hopefully that was another interesting lecture as we're slowly going through our journey in this material. Take care now. Bye-bye.